Now when we talk about the mass of an atom or a nucleus, we don't usually talk about kilograms, we talk about, just numbers. If we take helium, then we know that the atomic number is 2, but the mass number, say that the mass of one proton, if we actually have, we're saying that if we take our protons, neutrons and electrons, it has the higher the, that gives us 28.3 mega electron volt. Now when we talk about the mass of an atom or a nucleus, we don't usually talk about kilograms, we talk about, just numbers. If we take helium, then we know that the atomic number is 2, but the mass number is 4. Now what do we mean by mass number? Well, actually this is relative atomic mass. But it doesn't have a unit, does it? Well, in reality it actually does. The unit is the U. That is the relative atomic mass unit. Now what is 1 U equals to? Well, relative atomic mass is actually based off carbon, specifically carbon-12. Now carbon-12, we know, has 6 protons and 6 neutrons in it. So it has 12 nucleons. So what we say is, one of these has to be 1/12 the mass of a carbon-12 atom. So if you have an atom of carbon-12, that's protons, neutrons and electrons, then 1 U, that's relative atomic mass unit, is going to be 1/12 the mass of that. That must mean that we say that the mass of one proton is 1 U. 1 neutron is also 1 U. But in reality, these numbers aren't quite right. They're very, very close to 1, but if we actually measure them to a very high degree of accuracy, we find this. We find the masses to be 1.007276 U, and in neutron, it's actually even slightly heavier. Now you might say, well, it's pretty much 1. I mean, to 2 sig figs, it's definitely 1. But this is one of the very few times in physics where we have to go to a very high degree of precision, because the very small difference between these numbers actually makes all the difference. An electron, well, we say it weighs basically nothing compared to a neutron and a proton, but if we're talking about such a high degree of precision, then we need to take it into account as well. 0.000549 U. Now if we actually have an atom of helium, then we have 2 protons, 2 neutrons, and we have 2 electrons in orbit. What should the mass of this be? It should be equals to 2 lots of this, plus 2 lots of this, plus 2 lots of this. Okay, I probably could have factorized for 2, but this is just to show. It should be the mass of 2 protons, 2 neutrons, and 2 electrons added up together. Now when we measure the mass of a helium atom, we find it to be this number here. What's weird is that the separate masses of the protons, neutrons, and electrons don't add up to this measured mass. They actually add up to slightly more. That means that there is a difference in the calculated mass of a helium atom from its constituents, protons, neutrons, and electrons, and its actual measured mass. We have what we call a mass defect. So let's look at those numbers again. We have the mass of constituents, and that was 4.032980 U, and we had the actual mass of a helium atom. That was 4.002603 U. Now we can see that the constituents separated out weigh more than the actual mass of them put together in a helium atom, and that's always the case. The total mass of the constituents is always going to be more than the mass when in a nucleus. Okay, we are talking about electrons as well, but we're mostly concerned about what's going on in the nucleus here. Now let's find out what the difference is. If we take one away from the other, we end up with 0.030377 U. This is what we call the mass defect. We can give it the symbol delta M. So hang on a minute. So we're saying that if we take our protons, neutrons and electrons and shove them together, mass is lost in the process. But you should know from year 1 particles that if mass is lost, then it has to be turned into energy. How do we figure that out? Well, we do E, then take our mass defect, that's the mass lost, times by C squared. But the problem with this is that we have to convert it into kilograms first, before we can use this equation. So actually, we don't have to use that, and I'll show you why in a minute. So if mass is lost and converted into energy when constituents come together to form an atom or a nucleus, then it stands to reason that if we want to separate out an atom or a nucleus into its constituents, then we have to put that energy back in to regain that mass. And that is true. And we call this energy the binding energy. And the definition is it's the energy, no, we can say work as well. It's the energy or work required to separate a nucleus or an atom into its constituents. Yes, that's the same amount of energy that is released when we go the other way as well. And obviously, the bigger the atom or the bigger the nucleus, the more binding energy it has. The higher the binding energy for it is going to be. So, like we said, in order to use this, we need to say, take our mass defect in U, turn it into our mass defect in kilograms, and then E equals mc square it, and then we end up with joules. But there is a shortcut. Instead of having to convert to kilograms, we can go straight from relative atomic mass units into mega electron volts. To go the long way around, well, you need to times by 1.6 times 10 to the minus 27, then put that into there, times by 3 times 10 to the 8 squared, etc. But the easy way of going from U to mega electron volts is we times by 931.3. If one relative atomic mass unit of mass is converted into energy, that is the same as 931.3 mega electron volts. Mega electron volts being 1.6 times 10 to the minus 13 joules. So we have the mass defect for a helium atom, helium-4 atom. So let's try and find out how much energy that is. The binding energy for helium-4 is just going to be our mass defect in U, 0.030377, times by 931.3, and that gives us 28.3 mega electron volts. If we wanted to convert this into joules, we just divide by the conversion factor here. By the way, you get given this conversion in your formula sheet, but it's a useful number to remember to speed things up. You might be thinking though, if you always have to put in energy to separate nuclei into their constituents, then how do we actually get energy out of nuclear fission? Well, yes, you're right. So it's all to do with what's happening with the total binding energy, what's going into a nuclear reaction and what's coming out. So let's go with fission first.